All right, line A6, learning task 5, we're going to talk about the features of what we refer to as the Triac. And Triac is actually just a short name because the major actual name is much longer. At the very top of your learning task 5, we find out that the Triac is the common name for the bidirectional triode. That means it's going to have 3 connection points, thyristor. It's a bidirectional switching device, very similar in appearance to an SCR. It's very similar in the fact that we are going to go have 3 terminals off of it, but instead of us having an anode and a cathode, we are going to go and have MT and MT1, main terminal 1 and main terminal number 2. We are also going to go and have a gate, and if you look at the symbol that's on the inside over here, it looks as if it were back-to-back diodes or back-to-back SCRs. And in reality, that is what this thing goes and operates as. Your SCR was a unidirectional device. An SCR could, at the very max, only go and pass through a hump and a line, a hump and a line, a hump and a line, like that. If we would go and gate that thing so it would be fully on. We always lost when it was our SCR. I'll just draw this so that you guys make sure that you're keeping track of the fact that we're talking about SCRs over there. Our SCR always lost this lower second half of all of these waveforms. So it was great when we were dealing with DC, and we could use it for large amounts of AC, let it commutate and stuff like that. But we would have to use 2 of them if we wanted to go and have this second half. The Triac is bidirectional, which means that it passes current through in both directions, which means that any load that's connected to it is also going to go and see AC current that's going to go through it. And like the SCR, we're going to go and trigger this thing based off of time. If this is my sine wave over here, we can go and cut away just a little bit at the front of every single one of these, or we can cut away a little bit further into it to have less power, etc. We can vary, using a single Triac, we can vary an entire waveform from 0 to 100%, which is more useful to us than an SCR because we have to have 2 back-to-back SCRs in order to go and do that. Where the SCR does lack, though, is that the Triac does lack is that the Triac itself can't carry as large of currents. SCRs are massive. You can get forearm-sized SCRs, no problem, huge things that are going to carry bulk amounts of current. Triacs are going to be much smaller, and we are going to go and use them for relatively low current handling conditions. Usually we're going to go and use them for things that are going to be under like the 2,000, maybe up to about a 4,000 watt type of range. So ideally, we will usually use these things in things like light dimmers, or small motor drivers or something like that. They've got a couple of different leads that come off of these things. We talked about the fact that we've got main terminal 1, main terminal 2, and that we're going to go and have the gate, and they come in a bunch of different types of packages or configurations. These ones over here are just going to be a standard TO case that we're going to solder into something. Often cases, this piece over here is going to be attached to a heat sink. It's going to have to carry that heat out of the semiconductor device so that it doesn't go and overheat it. These over here are going to be for larger current applications. We're going to thread it in. Once again, note that this thing actually threads into the heatsink, which means the heatsink is live. Whenever you remove covers from electronic equipment, make the assumption that any heatsink that is inside the box is live. Very well could be. Might not be, but it very well could be. If it's on the outside of the box, guaranteed they have to have that thing attached to ground. But if it's inside of the box, it might be connected to something like this. We have our heatsink connected to it, and they might actually be carrying current directly through it. Be careful with it, is all that I'm saying. Gate terminal is also actually usually going to be a smaller one as well. If you take a look at this, you see that you've got the massive stud over here. We've got the main terminal 1, and we see that the gate is smaller. These ones, the TOs, are also small, that it really doesn't make much of a difference. Characteristics of a Triac are going to be similar to an SCR, but it's as if we have got an SCR that operates in both directions. We're going to go and have, if we go and have a forward value of voltage, we're going to have a small amount of leakage current that's going to happen through it because it's made out of semiconductors. But if we then go and turn it on, we'll be able to carry a lot of current through it. If we don't turn it on, and if we just continue to increase the amount of forward voltage, forward, we'll eventually reach a point where we go into breakover voltage, basically where we over voltage it and we just burn right across it. That can happen in the forward direction. The same thing happens in our reverse direction. In reverse direction, as soon as we reverse voltage, we'll get a little bit of leakage, but we can turn it on and properly conduct on the reverse side. Or if I keep it turned off, I can go and increase until I eventually go and break it over. Once again, this would be a bad thing. It just means we've broken it over in the opposite direction. We don't want to get to these breakover voltages. That's really not, the point of these graphs over here. We want to get to just enough voltage that we can go and turn this thing on and then operate it. So we're really trying to operate it inside of, these ranges right about over here. It is bidirectional, which means that we are not rectifying anything as well. We're going to go and pass through our AC. When our AC is positive, negative, we are going to be passing current through the circuit in this direction. When my AC goes negative, positive, we're going to be passing current through in this direction. And my load itself is always going to see that current switching around back and forth through. It is a true AC type of device. It is similar to the SCR that it does need to go and have holding current as well. We're going to go and give it a little pulse on the gate to kick it in. But once it is kicked in, we then just let this thing run until our holding current drops below value. Voltage drop across them is going to be relatively low as well. They don't take a lot of voltage. If I take a look at this, if I've got 120 volts, I'm going to see almost all of that 120 volts-ish over top of here. Really, we're going to drop, maybe 2, sometimes 3 volts over top. Well, the book says a bit lower, but in reality, they're usually a little bit higher. So expect to see, at the load itself, maybe like 118 with, 2 to 3-ish over top of that actual Triac. Looking at our ratings for these things, we're going to go and have a bunch of different ratings than the SCR, yet we're going to have some that are going to be similar as well. One of the ones I want to take a look at, once again, is this DVDT. It's the rate of rise. In other words, if I've got a really quickly moving, a high-frequency AC, then it's going to go and sometimes just shock this thing into conduction. As a result of that, they are limited to a much lower frequency. These things are actually much more susceptible because they can pass in either direction. So we can really only carry these things up to about 400 hertz. Remember that hertz is going to be the rate at which our frequency is changing. So that's going to be a high frequency. This would be a low frequency. If they're both reaching the same peaks, more or less, we see that this one's much more gradual at a lower frequency rather than this one, which is much more violent. It's that violent rise and fall that gives us that DVDT and turns these things on. So we're going to limit these ones down to 400 hertz and under is kind of the rule of thumb for them, which means that they're still fine for some stuff like AC drives. We don't really go a lot higher than that. But if we have to go to much higher values of frequency, and we definitely do for some of our applications, we are going to have to go up to an SCR. Other ratings that we're going to take a look at over here, the total maximum current, we're going to have to stay within the maximum current. And then we are going to go and have to keep it underneath the VRRM. VRRM is just going to be the breakover voltage that is going to go and turn it on without the gate signal. We don't want that to go and happen. We want to control. Otherwise, there's no point in having these things if we're just allowing it to go into conduction. So we're going to keep it well below the VRRM and above the IT. So we want our rating to be, we want to keep our ratings below both of these. Whatever our circuit is going to be, we want it to be less than this and less than this over here. Holding current, we're going to have a minimum value of holding current that we're going to go and have, and then we're going to have a minimum value of gate voltage and current. Together, we're going to go and provide these with gate power. We do need to have a small amount of watts at the gate, volts times amps, to go and kick it into conduction. There's all sorts of ratings that you can get out of these things, piles of different ratings that are going to be for, different maximum forward amount of current based off of different models. What we're seeing over here is a manufacturer's data sheet that would allow you to go and select one. And so what you would do if you were looking through something like this, you would say, hey, what is my maximum voltage that I'm going to go and be operating at? If it's 120 volts, you're probably going to want to take something from the 200 volt line. And then you're going to say, what's the maximum current? If your current is going to be 8 amps, you're going to be picking something from these ones over here because it's going to be greater than the 8 amps. So you just use it to size and pick these. And then based upon that size and the pick, you then can see a bunch of other characteristics. There's one line down here that we're going to talk about really quickly, and it's called the operating quadrants. Operating quadrants are something that is going to become more applicable to us as we get into our variable frequency drives here in a little bit. But I'm going to start by just moving this one out of the way for a second so that I can go and draw a set of quadrants. Everybody knows about, the quadrants, 4 quadrants where we have got a positive, positive, negative, negative. And we call this thing quadrant 1, quadrant 2, quadrant 3, and quadrant 4 that we are going to go and have over here. And what these are, operation just tells us about what we're able to go and use this Triac for. I'm going to go over these real quick and we'll cover them more in depth in VFDs, but this is what we call the forward motoring. Motoring quadrant. This one is what we call forward regeneration. This one is what we call reverse motoring. And this one is what we call reverse regeneration. And these values that we're looking at over here are going to be for volts. This is going to be my volts, positive volts, negative volts, and for current. Positive current, negative current. What these 4 quadrants describe is they're going to go and describe, and it's something you have to be familiar with later on, they're going to describe what we can use the semiconductor for. If I take a look at, let's say, this guy right over here, I see it's good across quadrants 1, 2, 3, and 4, which means I can use this thing to deliver power for forward motoring. Forward motoring would be where the voltage is in a positive direction across it, and the current is also traveling in a positive direction through it. So I'm using this thing to provide power to drive something. I can also use it for forward regeneration. That's where the voltage is still positive across it, but the current is being pushed through backwards. This would be for something like, you could use these for battery charging and stuff like that, where the current isn't following the voltage, but it's being shoved through by some other method. I can use it for reverse motoring. That's where my current is in the negative direction, my voltage is in the negative direction. So this thing is now going to be able to go and drive stuff in the opposite direction. And I can use it also for reverse generation, or regeneration, which is where my voltage is in the negative direction, but my current is in the positive direction. So once again, battery charging and stuff like that. Across the bottom over here, we see that almost all of them that they have are going to be able to operate across all 4 quadrants. Most of them are going to be able to do 1 and 3. They can drive stuff forward, they can drive stuff in reverse, they just can't handle doing regeneration. I see that these ones here can do both of that. This one over here is a little bit of an oddball because it's got 1, 2, and 3. It can do, forward motoring, forward regeneration, and reverse motoring. But usually you're going to go and find your semiconductors that they're either good for all 4 or they're good for 1 and 3, which means we can drive current and voltage together through it and current and voltage backwards through it. All the rest of these operating quadrants mean is that they can have forward voltage with reverse current and it's still going to be fine, or reverse voltage with forward current, it's going to be fine, or forward and reverse and reverse. It just tells us the type of current that they can take without going into any sort of a issue, a breakdown or anything like that. Triacs, case styles are going to come in a lot of these. I'm not going to go over top of this. Yep, you can order them in all sorts of different ones. You're going to go and order them. The larger that they are, generally the greater the amount of current that's going to go through them and the more heat that we are going to have to go and dissipate off of them. Full wave phase control using SCRs is going to be possible, which is where we are going to go and fire 2 SCRs back to back. And we covered this in the previous one where we said, hey, look, if we go with a positive negative, I would see that this one over here, I would be able to drive AC through here, and that would work. And then when my AC alternates negative positive, I would then be able to go and forward bias this one and drive my current back through in that direction. I could get current going through in that direction, as well as I could get current going through in that direction. But it's a bit more complicated because I have to go and combine my firing circuits and I have to have 2 individual SCRs, which means more connections and more points for failure off of them. It's much easier for us to go and throw in a single Triac, and a single Triac is just going to go and have, we place it in 3 terminals, one line, main terminal 1, main terminal 2, and then I'm going to go and have my gate terminal, and then I just need to go and have a small gate control circuit that is just going to give the pulse. On both the positive alternations, it's going to go and give a pulse, and on the negative alternations, it's going to give a pulse, and we'll be able to get that current through in both directions from these. Once again, really handy, but it's going to be really handy, especially for some of our small AC loads. Very similar to our SCR, we do also have to only provide momentary, just a little kick to our gate control circuit. It doesn't have to be continuous. It can just be a little pulse that we're going to go and blip out to this thing, which is going to go and drive it into conduction. Then as long as there's current through it, that's above the holding current value, it is going to go and carry through. And because it is still built in a lot of ways similar to the SCR, it's also going to go and commutate when that holding current drops below zero, which is really handy because all of our waveforms drop below zero 120 times a cycle, right? 60 hertz. So we're going to drop once going positive to negative and once going negative to positive. We can use these things to, once again, give us full control all the way from zero, where we've got it completely shut off, to full power, where we are going to go and allow more and more of that waveform through. Whether we're looking at SCRs or Triacs, what we're always looking at is we're looking at timing. How much of the waveform are we allowing to go through this? And based upon that is going to be the total amount of power that we are going to get out to our load itself. If we want to do with resistor control, we're going to be limited. Resistor control is really going to only allow us to go 50%. We can go do this with resistor control, so we can have it shut completely off, and then we can start to go and turn it on with resistor control, and we can get all the way up to here with resistor control, but that's going to go and be it. We can only do control from 0 to 90 degrees into that cycle that we're going to go and get. If we want to get full control, we're going to have to go back to that same resistor capacitor, RC type, that we are going to go and run through. It just gives us a much broader, we're just going to be trickling electrons onto that capacitor until it builds up enough voltage to give us that little kick through the gate. And when it gives a kick through the gate, it actually discharges that cap. Testing the SCR, testing the Triac over here. Triac testing is going to be very similar to what we would do with a SCR. You can try to run this thing off of an ohm meter if your ohm meter battery is strong enough, or alternatively, you could try to go and run this thing off with just a C cell or a D cell or something like that, and then just use an ammeter in line with it to go and measure it. Not very common that we're going to go and have these things isolated from the circuits. Usually if one of these fails, actually you can see it because it's going to be charcoaled, because it's the main current carrying device. Usually the control circuits are fine. It's usually going to be the main current carrier, the Triac or the SCR, that is going to go and be kicked out. But you can go and follow these steps over here. All you're going to do is you're going to go, because it's AC, you can connect to either side. You're going to go and make a connection across there, and then you are going to go and make a connection from the gate over to your MT2. As soon as you make that junction over to your MT2, so right now this thing should be reading open. And then once you make this connection over here, this thing should now be reading closed. And the way you would read it as being closed, if you had a battery in line with this, if it's going to be closed like that, you're going to have current flow through it. So amps are going to be going through it. This is going to be no amps. Then all you have to do, flip your leads around. So now you're going to go and have, your meter has been reversed. Once again, you should be reading at this point that it's going to be open. Or if you're using the ammeter, no amps. And then you're going to go and touch that gate over to your main terminal 2 once again. And then it is going to go and close, and you should have current amps that are going to be inside of the circuit. Once again, rare that your meter is going to be able to go and run this. Much, much more common that you are usually going to go and have this done with just an external power supply, or it's going to be done by an electronics tech. You're going to just pull the drive, and get these parts replaced by people that do this for a living. Okay, that's it for self-test, or for Learning Task 5. Get your self-test, and then it's on to other specialty viristors.